Hi, welcome everyone. In this session, we will discuss on computer system organization. To understand how an operating system manages resources, we must first understand the physical organization of the computer system itself. Modern computer systems are complex, consisting of one or more CPUs and a number of device controllers connected through a common bus that provides access to shared memory. These components compete for memory cycles, so the memory controller synchronizes access to ensure the system runs smoothly. When a computer starts up, a process known as booting, it requires an initial program called the bootstrap program. This program is typically stored in read-only memory or EEPROM, which we refer to as firmware. The bootstrap program initializes all aspects of the system, including CPU registers and device controllers, then locates the operating system kernel on the disk and loads it into memory. One of the most critical concepts in computer architecture is the interrupt. Because the CPU can only do one thing at a time, we use an interrupt-driven model to avoid wasting millions of clock cycles waiting for slow devices. When a device controller needs to communicate that it has finished an operation, it triggers an interrupt. The hardware sends a signal, the CPU stops its current task, and immediately transfers execution to a fixed location containing the starting address of the interrupt service routine, or ISR. To make this process fast, an interrupt vector is used. This is a table of pointers to specific interrupt handling routines. Once the ISR is complete, the CPU resumes its previous computation. It is also important to distinguish between interrupts and traps. An interrupt is usually hardware-generated, whereas a trap or exception is a software-generated interrupt. Traps can be caused by errors, like division by zero, or by a specific request from a user program for an operating system service known as a system call. Now, let's look at storage structure. The CPU can only pull instructions directly from its own registers and main memory. While main memory is the only large storage area accessible directly by the processor, it is volatile and too small to store all data permanently. To solve this, we use secondary storage, like hard disk drives and solid-state drives, which provide non-volatile, large-capacity extensions. Storage systems are organized in a hierarchy based on speed, cost, and volatility. At the top, we have the fastest and most expensive components, registers, followed by cache and main memory. Below those are solid-state disks, magnetic disks, and finally, the slowest and cheapest options, optical disks and magnetic tapes. Lastly, we have the EO structure. Every device controller is in charge of a specific type of device, and for every controller, there is a corresponding device driver in the operating system. This driver understands the controller and presents a uniform interface to the rest of the OS. For high-speed I/O, such as disk or network access, we use direct memory access or DMA. This allows the device controller to transfer an entire block of data directly to or from main memory without help from the CPU. Consequently, only one interrupt is generated per block of data rather than per byte, allowing the CPU to remain focused on other tasks. In summary, the balance of hardware and software in a computer system depends on interrupts for communication, storage hierarchies for speed and capacity, and DMA for efficient data transfer. Thank you for your time. See you in the next session. Bye.